Assalamu alaikum wa rahmatullahi wa barakatuh. Gentlemen, if you remember, in our previous class, we have started looking at the properties of fluid. Okay, we explained state, system, and property. And we looked at mass density, some useful facts about density, and specific weight or weight density. Okay, which is simply the weight per unit volume. So specific weight or weight density, specific gravity or relative gravity, and some few examples. Okay, variation of liquid density. So today we're going to start looking at shear stress. Okay. Today we'll begin to look at shear stress, which is one of the main properties of fluids. Okay, I have started explaining about shear stress before. Now we will take it in depth. Okay, so let me move on to the correct slide. Okay. Yeah, we reviewed. Now, pressure and shear stress. When you understand stress, many topics in mechanics, many topics in mechanics become easier, because stress is one of the most important aspects. Okay? The big picture is that there are only two kinds of stress. Okay? Normal stress and shear stress. This we explained before. Okay, in fluid mechanics, the normal stress is nearly always just the fluid pressure. That is the normal stress, which is acting. The word normal means perpendicular, acting perpendicular to a given surface area or to the body. Okay, so in fluid mechanics, the normal stress is always just the fluid pressure. And to the stress, we begin by noting that stress acts on material particles. Okay, for example, if you bend a beam, the material particles are deformed by normal stress. This we demonstrated previously. Okay. No, I think we even know. I demonstrated all this. We are to continue from viscosity. Yeah, from viscosity. I explained all this. The fluid pressure defined by PA and the shear stress defined by tau A. Okay, this I explained. Yeah, this is where we are going to continue. So 7 common fluid forces. Pressure force, this we explained. Okay, the pressure force caused by pressure distributions and is associated with pressure stress. We have shear force, okay, which is associated with shear stress, caused by shear distribution, shear stress distribution. This force requires the fluid to be flowing. Okay, we define fluid as substance that deforms continuously under the application of shear stress, meaning it does not resist shear stress. Fluid, okay, it's deforming continuously. And then we have buoyant force. We will explain the shear stress again after this slide. We have a buoyant force, which is having to do the force on a submerged, that is submerged or partially submerged body, that is caused by hydrostatic pressure. When you put something in water, okay, that it experiences buoyant force, which is the upward vertical force trying to push the body off. Okay, so it is also part of the is associated with pressure stress, and we have surface tension force, which is having to do with the forces between molecules. This will explain also in this chapter. Surface tension force, and we have drag force. When fluids flows over a body, the drag force is the component of the total force that is parallel to the fluid velocity. Okay, so when fluids are moving together, they tend to exert drag. Just imagine rubbing your hand, okay, rubbing your palms, okay, your palms against each other. So they tend to exert drag. The slow moving particle tends to like slow down the movement of the faster particle, because the particles do not all move at the same forward velocity. So for that, that is drag that is being exerted by the slower particles on the faster moving particles. This we will also explain in a short while. And then we have the lift force. When fluids flow over the body, the lift force is the component of the total force that is perpendicular to the fluid velocity. Okay, the drag force is parallel to the fluid velocity, while the lift force is perpendicular to the fluid velocity. Okay, and this is applicable associated with both the shear, the pressure stress and the shear stress. Though typically the effect of shear stress is negligible as compared to the pressure stress. Okay, though the shear stress is also very important because it affects the viscosity, the no-slip condition, which we are all going to explain. Okay, and then the thrust force, the force associated with propulsion, that is the force caused by a propeller, jet engine, rocket engine. Okay, so all this is called thrust force, and it's associated with the pressure stress and the shear stress. Okay, now viscosity. Let me open this. Okay. All right. Yeah. So viscosity now. If you remember in statics, we explained solid friction, okay, which is the force that opposes the relative movement between two solid bodies in contact with one another. Okay, we explained it, I think, in chapter 8 of statics, that is CE201. And we said that the force is proportional to the normal reaction, okay, and you have the coefficient of static or dynamic frictional force, which is mu. Okay, so friction occurs in solid, while viscosity is the equivalent of friction, but it occurs in fluid. Okay, that's liquids and gases. Okay, so viscosity is the measure of fluid resistance to deformation under shear stress. When you apply force to a liquid, of course, we define fluid as a substance that deforms continuously under the application of shear stress. So the resistance of a liquid to this shear stress is defined as viscosity. Some have some, definitely it means that viscosity is going to be a very small value, because we mentioned that fluid continuously deforms under the application of shear stress. However, the deformation, that is the extent of moving, the movement of fluid, either liquid or solid, is dependent upon the viscosity. Okay, it depends on the viscosity. For instance, if you have, let's say, honey, you know honey, acid, okay, and water. If you pour them on the ground, water will move faster than honey because honey has higher viscosity than water. Okay, so in other words, we will say honey has higher resistance to deviation under shear stress. Okay. Now, it is the shear stress developed between two layers in a fluid, okay, when unit velocity gradient exists between them. When you have two fluid layers moving, you know, in a given medium, I told you, they don't move with the same forward velocity. The velocity of the fluid at different levels or for different layers is different, okay? And this is because of the shear stress itself, or because of the viscosity, which we are going to explain, the no slip condition, which is like retarding. Some are being retarded. Those close to, okay, like for instance, if you take this example here, which we have, you have two plates moving, okay? Two plates moving. Okay, so for these two plates, the upper plate is moving while the lower plate is stationary. And you have a fluid in between. This is a fluid, let's say a liquid, it can be water. So the upper plate exerts force here, okay, exert force on the liquid. And if we consider this, the liquid is going to be deformed, okay? If we look at this to be solid, if it were to be solid, okay, this one that is moving is going to change, okay, because of the fact that the lower one is not moving, the upper one that is moving is going to change the position of the top, you know, from this, you can see it, then to this, okay? So it's going to be deformed, okay? So that is why, and here we define the, you have stress being proportional to strain, okay? For solid, okay, for solid, stress is proportional to strain, while for liquid, stress is proportional to rate of change of strain, okay? Stress is proportional to the rate of change of strain, okay? So now, if we have a liquid, I think we will even have another figure. Yeah, okay. Then now, the unit of coefficient of viscosity is Newton second per meter square, or kilogram per meter per second, or gram per second centimeter. Okay, this is not the SI unit. Okay, but this is the unit, Newton second per meter square. And here we say the stress is the shear stress is developed between two layers in a fluid when the unit velocity gradient exists. I will explain what is velocity gradient, okay, in the following slide. It is also known as absolute viscosity and dynamic viscosity. Okay, this will explain as well. Okay, the absolute viscosity and the, okay, absolute viscosity is dynamic viscosity. We have the other one, which is kinematic viscosity. Okay, and is denoted by letter mu. Now, studies have shown that the shear stress is proportional to the velocity gradient. This is the velocity gradient dv dy. Okay, so if you remove the proportionality sign, you introduce a constant, which is the coefficient of viscosity. Okay, so if you make it the subject, so mu is tau dy dv. Okay, so here mu is the viscosity. Another unit for viscosity is Pascal second. Okay, Newton second per meter square or Pascal second. Pascal is the unit of pressure. Tau is the shear stress, which is stress, which is a pressure Newton per meter square. Dy is the change in distance measured from the wall, and dv is the velocity. Okay, water viscosity at 293 Kelvin, that is 293 will be around 25 degrees Celsius, is 10 to the power of minus 3. But I think, let me check here. Just 1 minute. I want to double check something. There is a figure, but I feel probably okay. Yeah. Okay. All right. The figure is in the next slide. I will check it. All right. So depiction of strain caused by a shear stress, which is force per area in a fluid. The rate of strain is the rate of change of the interior angle of the original angle. If you consider this to be a solid surface, not moving, you have fluid in between, you have fluid flowing over it. Then when you consider an element, this rectangular element, when it flows, because of the fact that the fluid layers are not moving at the same forward velocity, so there is tendency that they can start at the same level, but over time, one will move faster than the other, isn't it? Because of the fact that the velocity of the upper layer is higher than the velocity of the lower layer. So that introduces the strain. Okay, so it changes. Okay, the fluid element, which may start this way, it will have to be deformed this way because of the fact that the velocity varies. You can see as you reach to the bottom, the lower plate, the velocity approaches zero because of the no slip condition. It is assumed that the particles in contact with the non-moving boundary, they stick to the boundary and become static, meaning they don't move. So that is the no slip condition. Slip meaning they don't like slide along the surface. So their velocity is zero because if they stick to the boundary, they will not move. So they have zero velocity. And that is because of the viscosity. Okay, because of the viscosity, because of the fact that the lower boundary is not moving. So they try to attain the velocity of that lower boundary, which is zero. And then they drag the layers above them, which are moving, which have velocity. Those layers, they have velocity. Okay, so they drag them, and that's why the velocity keep on, it increases up to the surface when it is highest. That's if the surface is not bounded by any other plate. Okay, so this is the rate of strain. So if you have a fluid element here, okay, so you have shear stress acting on both sides, both the upper, the lower side, and the upper side. And because of the fact that the velocities are different, so you see that after time t, the element here, this angle is deformed. Okay, this is the angle of strain. Okay, this is the angle of strain. And this happens because of the increase in velocity. Because here, the velocity almost remains, you know, this is V plus dV times T, and this is V plus V times delta T. So the distance traversed by this is given by V times delta T, while the distance traversed by the upper layer is V plus delta T, because the velocity is higher here, okay, because of this small change in velocity. Okay, so it has higher velocity. So that is what leads to the strain. So the no-slip condition, this I just finished explaining, that when fluid is in contact with a solid body, the velocity of the fluid at the point of contact is the same as the velocity of the solid body at the same point. Meaning, if the body at the contact, if the body is stick, the velocity is 0. So the fluid velocity will be 0. If it is moving, then the fluid velocity will be equal to the velocity of the solid body. Okay. This I will also explain again. This is a pipe where you have water flowing. Okay. You know, it is bounded by, you know, at all the sides. Okay, because it is circular. The cross section is circular. So the water particles in contact with the pipe walls have velocity 0. Okay, while as you move away from the pipe wall, the velocity is increasing. Okay, up to the center of the pipe where it is maximum, and then it begins to decrease. Okay, it begins to decrease. So here you have 3 points, A, B, C. Point A, the velocity here describes the speed of the material particle that is situated at A. Because of the no-slip condition, VA equals 0. Because the particles in contact with the solid body have velocity of 0. And for B, describe the speed of the material particle that is situated at B, and for C, it has the highest speed, okay? Because it is far away from the boundary. The boundary is where you have the shear stress to be maximum, okay? The shear stress is maximum at the boundary and reduces to the center where it is almost 0, okay? Because their velocity is maximum. Because the shear stress, what it does, it reduces the velocity. You know, just like friction. Friction reduces the velocity of moving bodies, okay? Friction reduces the velocity of moving bodies. Now, velocity profile, laminar flow, okay? Laminar flow is simply an ordered flow, okay, in which the particles move in streamlines, okay? The particles, they move in layers that do not somehow mix, okay? That do not somehow mix. They move in an ordered fashion, okay? That's why it is called laminar. That's layer, okay? Laminar is like they move in layers, okay? While the other one is turbulent flow, which is one in which, you know, the particles are just mixing. They don't move in a particularly defined layers, okay? And laminar flow is usually associated with low velocity, because it's only when the velocity is low that the fluid layers can move in a given fashion, that is in a given standard fashion, that, you know, they don't so much mix together, okay? So notice how information about shear stress can be deduced from velocity profile. All right, this is the same pipe, okay, in which water is flowing, okay? I mentioned before, shear stress is maximum at the wall because the slope is maximum, okay? Because shear stress, now, if you remember, is the slope of the velocity profile, isn't it? Is proportional to the slope of the velocity profile, okay? And this is the velocity profile. So the slope is greatest at the wall, okay? So that is why shear stress here is maximum. When you go to the center, shear stress is 0 at the center line, because the slope here is 0, okay? Because at this point, you don't have any change in the velocity, okay? dV becomes 0. And here, when you are coming back as well, the shear stress at any point is proportional to the velocity gradient. which in this case, in radial coordinate, we use the R. Okay, because here we have the radial coordinate. We have the axial location, the radial location. Okay, so this is the axial, this is the radial location. So here the radial is the axial, this is the radial. So R here, this is 0, and then it increases this way. Okay. So which is the slope of the velocity profile? So the shear stress at any point is proportional to dV dr. Now, Newtonian and non-Newtonian fluids. Fluids that have constant viscosity are called Newtonian fluids. Okay. However, fluids with variable viscosity are called non-Newtonian fluids. Okay. Now, in this course, we will deal with Newtonian fluids only, that is constant viscosity. Okay, when you have the shear stress plotted against the velocity gradient, okay, fluids that are Newtonian fluid will have a constant shear stress. Okay, the slope is going to be constant, or is going to be, the plot is going to be linear, the plot of the shear stress versus velocity gradient. Okay, and it starts from the origin. It starts from the origin. So this Newtonian fluid. Okay, Newtonian fluid. You have Bingham fluid, plastic, which does not start from the origin, but the shear stress is proportional to the velocity gradient, and it is linear. Okay, and you have non-Newtonian fluids. Okay, you have shear thickening and shear thinning. Okay, if you look at the plot, they are non-linear. Okay, so Newtonian fluids is one that obeys the Newton's law of viscosity, which is the fact that the shear stress is proportional to the velocity gradient. Okay, and when you remove it, you have a constant dV dy. Okay, so the viscosity is constant for Newtonian fluid, which is mu, while for non-Newtonian fluid, the viscosity is not constant. It will be the viscosity here, which is the mu, is simply the slope. It's simply the slope of the graph. Okay, because here the slope is change in the shear stress over change in the velocity gradient. Simple. Okay, which is mu. Okay, so it will be constant if it is linear. But for those that are not straight lines, they are not going to be constant. Okay. Now, another thing to explain here is what is called Couette flow. Okay, which is used as a model for a variety of flows that involve lubrication. Okay, Couette flow, a moving surface causes, in Couette flow, a moving surface causes fluid to flow. Okay, a moving surface causes fluid to flow in Couette flow. Okay, we will show a figure to demonstrate that. When the viscosity equation is applied to Couette flow, the derivative can be replaced with a ratio because the velocity gradient is linear. Okay, let me explain this. So in Couette flow, you have a fixed plate, very important, fixed plate, and you have a moving plate. Okay, fixed plate and moving plate. And then we mentioned that for Couette flow, the moving surface causes fluid to flow. So this moving plate, moving with a force F, is causing the fluid to flow. Okay, and this is the velocity gradient, which is linear. Okay, the velocity gradient is linear, unlike what we normally have, which is curvilinear. In Couette flow, it is not curvilinear. It is not curved. Okay, it is, the velocity gradient is linear. Okay, and in that case, this V1 equals 0 because it is at the bottom, and V2 is the maximum velocity here. Okay, and for small v and y, velocity profile is linear. Yeah, for small velocity and small depth, okay, the velocity profile is linear. And in Couette flow, the shear stress is constant. Couette flow is different from Newtonian. In Newtonian fluid, we said the viscosity is constant. In Couette flow, we said the shear stress is constant. Okay, if the shear stress is constant, then we don't need to use derivative in this case. Okay, because it means mu is just v over y, which is the velocity, okay, over the depth. Yeah, we will take a simple example to demonstrate the QED flow. So in this example, it says applying the viscosity equation to calculate shear stress in a Poiseuille flow. Okay. So we have flow inside a pipe. Okay. So the problem statement says that a famous solution in fluid mechanics called Poiseuille flow involves laminar flow in a round pipe. Okay, laminar flow. You have different types of flows, and most of them are affected also by viscosity. You have laminar flow and turbulent flow. You have compressible flow and incompressible flow. Okay, incompressible flow. Of course, I told you all liquids are almost incompressible. Okay, they are almost incompressible, and then compressible flow when the fluid particles are compressible, like in gas. You know, for gas particles, they are all compressible. So you have compressible flow in that case. But then we will explain another instance in which the flow can be somehow compressed. By compressible flow or by incompressible flow, it means the density of the liquid remains the same throughout. Because if the density remains the same, then it cannot be compressed. Remember, density is the mass per volume. So if the density of the fluid particles remain the same, then the flow is called incompressible. Okay, we'll explain a special case of liquid flow or water flow in which there is like local compression. The density like reduces because of abrupt closure of a valve or so. So that leads to what is called water hammer. This will explain in few slides to come. So here, consider the Poiseuille flow with a velocity profile in the pipe given. Okay, so this is the formula for the velocity profile in radial coordinate in terms of the radius. Okay, you can see that. So this is V naught. Okay, over R naught. R naught is constant, V naught is also constant, which is the velocity at the center of the pipe, where R is the radial position as measured from the center line. V naught is the velocity at the center of the pipe, and R naught is the pipe radius. Find the shear stress at the center of the pipe. Okay, find the shear stress at the center of the pipe at the wall and at where R equal 1 centimeter. Okay, and the diameter is 4 centimeter and V naught is 1 meter per second. Okay, so the only variable we have is R. V naught is constant and R naught is also constant. Okay, so here to calculate the shear stress at these 3 points, we simply substitute R, isn't it? Because it's the only thing that is variable. The first, find the shear stress at the center of the pipe. At the center of the pipe, that is the origin where R is 0. So R equals 0. Okay, so when we now try to substitute, and then when R equals 0.01, which is at the middle of the pipe, somehow just slightly away, okay, from the center, okay, of the pipe. And then we have at the wall when R equal 0.02. Okay. So to do that, we need to find the velocity gradient, which is differentiating this velocity function with respect to R. Okay, with respect to R, and then substitute in the formula, because we know that the shear stress is simply the viscosity times the velocity gradient. In this case, dV dr. But then there is another caveat to this. If you look very well, in the previous instance, when we have dV dy, when y increases, dV dy, yeah, when y increases, the velocity increases. But in this case, when r increases, the velocity reduces. So when we are using R here, we use minus sign so as to ensure that the shear stress is a positive quantity. Is that clear? When you are using dV dy, you don't use the negative sign because the velocity is proportional to the depth. Okay, as the depth increases, the velocity increases. But in this case, when you have a pipe flow, the velocity is inversely proportional to the radial distance, because the radial distance starts from the center of the pipeline. So when the radius increases outward, the velocity decreases. So it's inversely proportional. So we introduce a negative sign here so that, because this quantity is going to be minus, so minus will cancel the minus, and then ultimately shear stress will turn out to be a positive quantity. Okay, so this is a very important point that you need to take care of. Okay, so now we need to find dV dr, that is differentiate this with respect to r, and this is very simple. Okay, so this is my explanation. The sign change occurs when the variable is changed from y to r. Okay, so dV dr, you did a differential calculus math 101, very simple. Don't forget that V naught is constant. Okay, so when you differentiate this, you have, I mean, it's a very simple problem, which when you open the bracket, okay, you have V naught minus V naught into R squared over R naught squared. Okay, and then when you differentiate dV dr, this is constant, which is 0. When you do this with respect to r, so it's going to be 2r minus 2 v naught r. Okay, then divide by r naught square. Remember, this r naught is a constant. Okay, so this is the only variable. Okay, so that's why you have it here. Okay, so now having obtained our velocity profile, I mean the velocity gradient, you can just use, because shear stress minus mu times dV dr now. Okay, so although here we determine at r equals 0, so we substitute r equals 0 in the equation to find the velocity gradient, and then substitute the velocity gradient. We multiply the velocity gradient with the viscosity, okay, in this, okay, to get the viscosity, to get the shear stress. Of course, at the center, the shear stress is 0. So you may not even need to make this substitution, but to prove that yes, it is 0, maybe if you substitute and realize it's not 0, definitely you know that you are wrong, okay, but definitely it must be 0, the shear stress at the center point of the pipe. Okay, and at r equals 0.01, we found the velocity gradient, and then we substitute the formula to find the shear stress. Okay, then at r, at the wall is going to be highest. Okay, the shear stress is highest. You can see at r equals 0.01 is 0.05. Here is 0.1. Way higher than at r equals 0.01. Okay, so now another simple example. Here we have for the current flow. Still have some few more minutes. You have a board. Let me hide it. A board which is 1 meter by 1 meter. It weighs 25 Newton. This is like the front view, and this is the board. Okay, it weighs 1 meter by 1 meter, meaning it is, you know, like this. Okay, okay. So placed, you know, on the ramp. So slice down an inclined ramp at 20 degrees Celsius. So this is the angle, with a constant velocity of 20 centimeter per second. Okay, so this is the velocity of flow of movement. The board is separated by the ramp by a thin film of oil Okay, so you can see there is some small distance between the board and the ramp. Okay, and you have oil whose viscosity is 0.05 Newton second per meter square. Assuming that the oil can be modeled as a cured flow, calculate the space between the ramp and the board. Okay, so with very short space between the ramp and the board. Okay, so it says it can be modeled as a cured flow. So in this case, we have the data. We want the thickness of the oil, H. We were given the viscosity of the oil, okay? And we were given the dimension and the weight. So we have to go back to statics and draw the free body diagram. Okay, since it is cured flow, and remember in cured flow, uh, yeah, the shear stress tau is just mu Vy, okay? So in this case, tau is mu Vy now, which is the depth is going to be h in our own case. So making h the subject of the formula, you have it to be mu V naught over tau. Okay. So here V is given, which is constant velocity, of the board. This is constant. Okay. Which is the viscosity of the fluid, and this we need to find. Okay. The shear stress. Okay. Once we know the shear stress, we can substitute in this formula to find H. Okay. So to find the shear stress, we need to find the shear force. And the shear force here is simply the friction. Okay. It's simply the friction which is trying to oppose the movement. Okay. The relative movement of the board over the liquid. Okay. So we draw the free body diagram of the board. Okay. Weight will be acting vertically downward. Okay, this is the weight. And then we have the normal reaction because it is because of the inclined plane. So the action N. And then we have the shear force acting in the opposite direction. Okay. And the shear force is given by the shear stress times the area. And we know the area of the board is 1 meter by 1 meter. Okay. So first we can find the shear force. If we find the shear force, we can now get the shear stress. Okay. Now from this, when we resolve, this is 20, this angle is also 20. Okay. This angle, okay, if we take it vertical, if we take it this way as well, this small angle is also 20. Okay, so now we will resolve the forces either horizontally or vertically. Okay, to get applying the equilibrium equation, summation of forces in the horizontal direction. Okay, in the horizontal direction we have W sin theta. In the horizontal direction, that is along this plane. Okay, we have W sin theta, if we call this angle theta, okay, W sin theta along this plane, and then minus or is equal to the shear force, okay, which is, this is the shear force F, okay, tau A, okay, and this will now enable us to obtain the shear stress. Theta is 20, okay, so here we can find the shear stress, okay, using the equilibrium equation. So this is the shear stress, and then we can simply come here and substitute it to get H. Very simple. Okay, H is about 12% of a millimeter, so this is very, very small. So that is why statics is prerequisite to fluid mechanics. Okay, because this is simple application of static principle. If you remember this, okay. This we did, when explaining friction and things to do with that. Now, Any question on this? Is it very clear? Hello? Okay. Let me check your responses. Oh, what is not clear? Mohannad. You can talk. I enabled your mic. Oh, clear. All right, good.
I think he mean no question.
What?
I think he mean no question. They have no question.
Oh, all right, all right, all right. So variation with temperature. Viscosity, as we can see, reduces, with temperature. Okay, the viscosity as the temperature increase, the viscosity, this crude oil, the viscosity reduces. Okay, and it increases with air or atmospheric liquids. Increasing temperature decreases viscosity. Why? Increasing temperature decreases viscosity. Because when you increase the temperature, you are imparting more energy to the fluid particles, and then they will be more energetic to move. They will expand, and then their ability to move becomes enhanced. Okay, so their resistance to shear stress, reduces greatly. So that is why increasing the temperature, it decreases the viscosity of liquid. Okay, and gases. For gases, increasing the temperature increases the viscosity. For gases is the reverse. Okay? For gases is the reverse. When you increase the temperature, their viscosity increases. So why is that? For gases, when you increase the temperature, the rate at which they collide, you remember gases are in constant motion. They're in constant motion, and they collide with one another and with the walls of their containing vessels. So if when you increase the temperature, that collision increases. It becomes more rapid. Okay, the number of collisions per second increases. Okay, and that leads to the increase in the viscosity of the gases. Now, variation of liquid viscosity with temperature. Okay, we just mentioned that it varies with temperature, and then how does it vary? It can be mathematically computed. The viscosity C exponential BT. So here you have constants, B and C, which are empirical constants for each fluid. Okay, you can determine the viscosity at any given temperature. I just substitute it once you know the constants C and B. Okay, and table A3 shows the variation of viscosity with temperature. And for gas, the variation of gas viscosity with temperature can be defined. This is for gas. Okay, where you have T is the absolute temperature. Okay, this is Sutherland's constant. Mu is the viscosity at temperature T. Mu net is the viscosity at temperature T naught. So mu is called viscosity or absolute or dynamic viscosity. It's called absolute or dynamic viscosity. We have another viscosity which is called kinematic viscosity, which is defined as the ratio of the viscosity to mass density. Okay, viscosity, that is mu over the mass density. Okay, and this is due to the rapid occurrence of the ratio mu over rho in many equations. Okay, so this ratio has been given the name kinematic viscosity. Okay, and the unit of the kinematic viscosity is meter square per second, or centimeter square per second, or stock. Okay, and this is the symbol. Okay, for the mu. Okay, mu. This is mo. Okay, mo. Okay, this is mu. This is mo. Okay, so the kinematic viscosity is given by the absolute or dynamic viscosity over density. And the unit of this one is Newton second per meter square. This one is Newton second per meter square, while this one is meter square per second. Okay. Now, oh, my time is up. Bulk modulus of elasticity. So in our next class, we will look at the bulk modulus of elasticity, which is going to be tomorrow. Okay. Any question before we call it a day? Any question? All right. Thank you so much. See you tomorrow at 9. Okay. And tomorrow, and remember, tomorrow we will have our first quiz. Okay. Our first quiz holds tomorrow. Okay. And I said it was going to cover up to where we stopped last week. Okay. That was up to just before viscosity, slide 35. Okay. Up to slide 35 of chapter 2. Okay. Yeah, it is going to be during the lecture. It is going to be during the lecture, at the end of the lecture. Okay, so up to slide 35. Okay, the quiz will cover up to slide 35. That is, about shear stress, or let's say, all right, let's say up to slide 27. Yeah, up to slide 27. Okay, up to slide 27. Okay, yeah, up to slide 27. All right, see you tomorrow.